So from last time, we saw how you move from a representation of your group into a representation of your L1. So basically, I call the integration theorem. So you integrate against your L1 function by the operator value integral. And in this video, I'm just going to finish off this lecture by doing the converse. Basically, you also have a disintegration theorem. So as long as you have a non-degenerate continuous star representation of your L1 of G, then you can always kind of decompose it as an integral of some unitary representation. Okay, so this is essentially what this proposition is saying. And this representation pi is actually going to be unique. Okay, so I should mention this pi is unique. So let's do it this way. So moreover, this pi is unique. Okay. So in other words, every non-degenerate continuous star representation arises from an integral of some unitary representation. Okay. So I really like the proof. Okay. So it's kind of very neat. So let me give you the basic idea first. So first of all, let's consider the span of these I functions. So I is some star representation of my L1 space. So if I take all the I of f and I evaluate at some h, okay, so here f is inside L1 of G, h is inside h. So let's give it a name. Let's call it the span of them. Let's call it equals to m. Okay, so first of all, I want to show that m is going to be dense in H. So then, first of all, the m is dense inside H. Okay, why is that? Well, suppose you have some vector. Well, suppose it's not dense, so you take the closure that's not equal to the entire H. So in other words, well, right now you're living in a Hilbert space. Basically, you have something that's non-zero, that's orthogonal to everything inside M. Okay, so there exists some V inside this H, so that V is orthogonal to M. So in other words, if you take any F inside the L1 of G, and you take any H inside this H, then this I of F evaluate on H is going to be orthogonal to this V. Okay, so this is going to be equal to 0. But the good thing about things on Hilbert space is that you can always move the I to the other side. So in other words, this H, if you take the inner product of H with the adjoint of the IF with V, that's also going to be equal to 0. But I being a star homomorphism, so this is I of the F check of V, that's going to be equal to 0. But now the H is arbitrary, so H is arbitrary. Well, you're in a Hilbert space. That just means the IF check of V has to be equal to 0. So that implies the IF check of V that's going to be 0 for all F check. Okay, but well, F check the involution of the involution is the function itself. So this just implies that the image of the L1 of G under I is going to annihilate this V. So that's going to equal to 0. But because your I is non-degenerate, the V has to be equal to 0. Okay, so by the non-degeneracy, then I have this V has to be equal to 0. Okay, in other words, its orthogonal complement can have nothing. So basically it says this M is dense. Okay. So because this is dense, okay, so let me just recall there's one algebraic property we proved from last time, is that if I take the pi of x and I evaluate on I pi of f, then that should return me the I pi of the left translation by x, okay, the f by x, okay? So in other words, if I think about this I, if this I is some I pi, well, then the pi, if I want to integrate into this pi, if I want to recover this pi, then the pi, when you evaluate, so if I say pi x, and I evaluate some vector, say I pi f of h, then I really have no choice. I have the I pi of the LXF evaluate h. Okay, so my pi is really fixed on this dense subset. Okay, in other words, there's only one choice for my pi. Okay, so this is kind of the neat idea behind this proof. So if I just let pi of x for every x, of some vector inside my dense subspace, which is M. So it's a linear span of these I function of IFN evaluate times HN and going from 1 to some say M. Okay, I just define it to be the summation of I going from M of I of the left translation of these Fn evaluate Hn. Okay, so this is essentially the only choice I can have for my pi x. Okay, there is really no other choice. And if this pi defines a unitary operator on this dense subset, then I can use the continuity to extend it to a unitary operator on the entire H, and that should work. Okay, so the only thing I need to check is that this pi is really going to be a unitary. Well, this pi clearly has an inverse. Okay, just apply the left translation by x inverse. So let's just show this is an isometry. Okay, that should suffice. So to see this pi x is an isometry, I basically just need to evaluate the length of this vector. Well, the length of this vector is fairly simple. So let's say the summation n going from 1 to m of this I function of the left translation of the Fn evaluate on Hn. So this one is, you can think about it as the inner product of this with itself. So this is really just the double summation of, let's maybe just change it to n and k, of the, I have the I function of the left translation by x, it's the same x, but then I have the Fn first, evaluate on Hn, and then I have the left translation by x of the Fk, evaluate on HK, and then you do the inner product. But the good thing is that, well, the I, is a star homomorphism. It's a continuous star representation, so you can move the I to the other side. So this is going to be the double summation on n k from 1 to m of the I function of the left translation of the Fk, and you take the adjoint of this operator, multiply by I of the Lx Fn, evaluate at Hn and Hk, okay? And again, this F is a star representation, so you take the adjoint is the same as you evaluate on the involution of the function. And then when you multiply is basically evaluate the I on the convolution. So this is, if you write it as the I function of the Lx Fk involution, and you convolute with the Lx Fn, you evaluate Hn Hk, okay? And so what is this involution? Okay, so if you look at this involution of Fm check with Lx Fn, if you evaluate at y, so this is just no other than the integral of the Lx Fm check, evaluate at some say t, and then you have Lx Fn, evaluate at t inverse y, and then you do the dt. Okay, the idea is that because the m and n they're both translated by the same x. Okay, so because the integral is going to be left translation invariant, this whole integral is basically the convolution of Fn and Fn. Okay, so let me just write a bunch of integral. So that's the idea is this. So let's say this by definition. The first one is the delta t inverse. I have the Lx Fm of the t inverse, the whole thing conjugate, and you have the Lx Fn t inverse of y dt. And then because of, you can use the, let's just write out the Lx first. So this is t inverse. I have the Fm of x inverse t inverse. And then you have the Fn of the x inverse t inverse, and you have a y, and then dt. And then from there, you can just use the translate. Well, first of all, let's remove the modular function by changing the t to the t inverse. So this is the integral of the Fm x inverse t, and then you have the Fn of the x inverse t y dt. And this is just essentially the integral of the Fm conjugate, okay, Fm t conjugate. and then I basically conjugate here and there, and then you have the Fn of the Ty dt, okay? So this one you can write it as the integral of the Fm T inverse. Let's move everything back to the T inverse. Delta of the T inverse have the modular function, and then I have the T inverse y dt. But this one, the first part is the m check at T, and then you have the Fn of the T inverse y dt. So basically you remove the x inverse, okay? You remove the translation by x. So this is the Fm check convolute with the Fn, you evaluate this whole thing at y, okay? So in other words, so what we proved is that each of these left translation, because you translate left on either side, they actually just cancel, okay? So let's just plug into this formula. So let's replace all of these by removing the left translation by x. So what we proved is essentially the following. So I started with the summation of the I of Lx Fn Hn, okay, this whole thing squared, and I end up with is basically this double summation of a bunch of I of the Lx Fn check convolute with the Lx Fm, well, I should say M first and then N next, or I think I use K first. And then, anyways, I have Hn and Hk, they're in the product. And now I proved I don't really need the left translation. I can just pretend this is the I function of the Fk check convolute with the Fn, evaluate on Hn in the product with Hk. Okay, so Hk. All right, so but this one is essentially the same as the summation of the I of the Fn Hn, this norm, okay? So in other words, this U map, okay, so U, remember, is, well, or this pi x defined as this vector mapped to the other vector. So in other words, this pi x is an isometry, okay, so it's isometry. So because it's an isometry, so it's clearly bounded on a dense subset, so it extends to an isometry on the entire space H. So we can say this pi now is defined from G to the B of H is basically extend. So extend each of these pi x. So this is an isometric representation. And because of pi x inverse times pi x is equals to pi of the identity, which is clearly going to be extended to the identity. So if you plug in x equal to identity, you see it doesn't really do anything. So everything is invertible, okay? So if you have an invertible isometry, you have a unitary, okay? So pi is indeed a unitary representation. So we also need to check the continuity. So suppose I have some x alpha converge to f x inside G. Then we showed before that the left translation is also continuous respect to the L1 norm. So the left translation by x alpha is also converging to the left translation by x, okay? So, and because you have your, the I function is going to be continuous, I is a representation. So if you consider this pi of x, okay, if I evaluate at any h, and if I take the difference between pi of x alpha evaluate at h, let me just wave my hand a little bit. So here, because your the span of these I function evaluate on h are dense, so you can approximate this h by some I function, some summation of I function evaluate on h. Okay, so this is approximated by the pi of x minus pi of x alpha evaluated on this summation of I of some Fn Hn, okay? So that norm. But this one is just essentially the same as the summation of the difference between the left translation by x of these Fn minus the left translation by x alpha of these Fn. I should just probably move into the same I. So I have this left translation by x alpha of xn, and this whole thing evaluate on Hn, and I take some finite sum. So here n going from 1 to m, so finite sum. And because of these left translation conversion L1, your I norm is, well, the I representation is also contracted respect to the one norm. So this one is going to 0. Okay, so this should be a 3 epsilon argument, but essentially you can show that this pi is also SOT continuous. And so basically now we prove that there is a pi, which is unitary representation. So pi is a unitary representation. And so we just need to show that it integrates to the same thing as I. So one thing about this is that if I consider the convolution of two things, so f and g, so one way, of course, this is the integral of the, say, f of x of g of x inverse, let's say, evaluate y. So g x inverse of y dx. Okay, and you can also treat it as a function valued integral. Okay, so you can think about this function as the integral of your function f of x, and you left translate your g. Okay, and then you do the dx. Okay, so because your I function is going to be linear, so this, if you apply the I of the f convolute with g, that's just going to be equal everything passed through. Everything is linear, integral is linear, so you really do the integral of the f of x times the I function of the Lxg dx. Okay, so they are going to be the same. And what is the Lx of g? Well, by our definition, this is going to be this part is going to be equals to the pi x times the I of g. Okay, the pi x will map I of g to the I of Lx of g. So this one is essentially going to be integral of fx pi x. I have the I of g dx. And now I of g just goes out, okay? It doesn't depend on x, and you end up with the integral of the fx pi x, which just essentially equals to the I pi of f, and then you have I of g. So essentially this proves that the I function of a convolution, of course, this is on the other hand, because I is a star representation, this is IF IG, but you can replace the first I by the I pi, the integral of this representation pi, which is built. But from there, you can see that if you take I pi of f, okay, if you evaluate at any, say, summation of gn hn, okay, because this I pi of f times the I of g are the same as I of f times I of g, so this is the same as I of f evaluate on the same summation, I of gn hn, okay? So because they're the same, well, and they're the same on a dense subset, so these two have to be the same. So I pi is equals to I, okay? So this finished the last bit, okay? So this pi we actually found, they actually integrate to the same function. This pi will integrate to the original I. And just want to point out this pi has to be unique. The reason it's unique really just come from that our definition. So from our definition of this pi, it has to map this vector to the other vector. That just comes from the property we proved from last time. Okay, as long as you have I is equal to I pi, then this pi has to map this vector to the other vector. So it's kind of fixed on this dense subset. Okay, so the uniqueness just follows from there. Okay, there's no other choice as long as you have two representation that agree on a dense subset, then they have to be the same operator. Okay, so this finished the proof of the disintegration.